Okay, this video is going to walk you through solving the Schrodinger equation for a particle in a box. Now this is our first application of the Schrodinger equation. So I'm going to walk through explicitly the solution for this. You're going to see that it's very similar to what we did when we solved the wave equation earlier. Just to note that you'll also see the particle in a box problem referred to frequently as the particle on a line or a particle in a square potential well. So there's a few alternative names for it, but basically what we have is a particle that is destined to spend its life inside of a box. Okay, so why do we care about a particle stuck in a box? Well, first of all, it's the simplest application of the Schrodinger equation that we can work with, so we like it for that reason. It gets us started kind of nice and easy with applications of our Schrodinger equation. It does offer some physical insight into more complicated problems, so you'll see applications of this particle in a box theory to a number of areas. Specifically, we'll see application for it to the pi electrons in conjugated hydrocarbons, which is going to be the lab that you do related to this topic. So you're going to apply the particle in a box model to a bunch of conjugated dyes, and you're going to see how well it works. Okay, so basically this is just our simplest example of utilizing the Schrodinger equation, and that's why we are starting there. Okay, so let's set up our problem. So we're going to picture a particle of mass m, and that particle is free to travel along our x-axis here. So our particle is traveling freely between our boundaries of 0 and a. All right, so when the particle is inside this box, we will assume that the particle does not experience any change in potential. Okay, so that means that we'll say our potential energy inside the box is 0. Okay, so our u of x is 0 for inside the box. So our particle experiences no change in potential. However, outside the box, okay, so once the particle gets to these endpoints, here are walls of our box, we see that it experiences this infinite potential or infinitely repulsive barrier. Okay, so we have that at x equals 0 and x equals a, so at both of our bounds of our box. Okay, so picture yourself as this particle inside of a box, or picture yourself inside of a room that has infinite walls. Okay, would you ever be able to escape that room? No, right? There's no way that you can possibly jump over or escape over an infinitely high wall. Okay, so that's essentially the problem that we're setting up here. So we have a particle that's stuck in a box with infinite potential walls. Okay, so basically what we have done there is to guarantee that our particle is stuck in our box for all of eternity. So kind of sad for a particle, but it is what it is. Okay, so inside our box, remember we say our potential energy is 0 for our particle, and then outside of our box, our potential is infinite. Okay, so particle is stuck inside the box forever, or forever if we want to pretend we're in a yearbook. Okay, so let's get down to the business of solving our Schrodinger equations for these different regions of our particle in a box problem. So we're going to break this down into regions 1 and 3, where we have our infinite potential, so that's outside of our box, and then we'll treat region 2 separately, and that's where we have our zero potential. Okay, so starting with regions 1 and 3, we're going to set up our Schrodinger equation. So remember, we want our H psi equals E psi here, where we're going to plug in for our Hamiltonian. So we want our kinetic energy operator minus h bar squared over 2m d squared dx squared, and then our potential energy operator, we'll just call that u of x for now. Those will combine to make our total energy operator, our Hamiltonian. Remember, we have to multiply that by, have that act on our wave function psi of x, and then that's going to equal our total energy times our wave function again, and that's our initial setup of the Schrodinger equation. Okay, so let's just remind ourselves here that this quantity right there is equal to infinity. Remember, we have an infinite potential in our regions 1 and 3. Okay, so let's think about that. So we have an infinite potential here. If we compare that to our kinetic energy term, right, that infinite potential is going to dwarf anything coming from this, right? So we can just simplify that a little bit and write our Schrodinger equation like that. If we bring our infinity over to our other side, okay, just a little algebraic magic, we get that result. Okay, so let's think about this. We have a quantity, our wave function is now equal to a quantity, our total energy times our wave function, but we are now also dividing it by infinity, right, due to our potential energy term. All right, so again, infinity is going to dominate here, so our wave function is basically 1 over infinity, which means that our wave function is basically going to go to 0. Okay, so one thing to always remember is that when your wave function equals 0, okay, that is not a very interesting problem for us, because that just means that our wave function does not exist in that area, which is fine, right? It's just not a very interesting problem. Okay, so in regions 1 and 3, our wave function is 0. So for region 1 and for region 3, we have no particle. Okay, so there's our end result there. So nothing interesting for us to work with in regions 1 and 3, which goes with the problem that we set up, right? We have no particle there, so thank God the wave functions there are actually 0. Okay, so now hopefully we'll get something a little bit more interesting for region 2, so we have something to do with ourselves. All right, so once again, we'll set up our time-independent Schrodinger equation for region 2. So remember here, our potential energy we said was 0. Okay, so we'll just plug that into our Hamiltonian. So same kind of idea. Plus, I'm just going to plug in right away our 0 for the potential. Equals E psi. All right, so there's our Schrodinger equation for region 2 with our 0 representing our potential energy, part of our Hamiltonian operator. Okay, so we will just, again, simplify this a little bit, get rid of that zero potential. I'm just going to bring everything over to the left-hand side of our equation. Okay, so we'll just do a little bit of rearrangement here. And we'll just remind ourselves that we're in region 2 there with our wave function. Okay, so this magic arrow here is just some algebraic rearrangement of our equation, so bringing everything over to our left-hand side, and a little bit of moving around of our constants lets us end up with this equation. So maybe pause the video, take a second, just kind of go through that transformation yourself, verify that we end up there, and then hopefully something looks familiar to you when we look at this equation. So hopefully this is screaming out to you that we have our magic HLDECC form of equation that we know and love from solving our wave equation. So remember, I promised you that we would see that wave equation solution rear its head again, and here it is. Okay, so solving the Schrodinger equation for the particle in a box model is extremely similar to what we did for the wave equation. Okay, so we're going to take our HLDECC equation that we just obtained from setting up our Schrodinger equation for region 2, and we're just going to remind ourselves that we saw when we worked with the wave equation earlier that we already know the general solution to this form of equation, right? So we've seen all of this before. Okay, so we know that the general form of our HLDECC solution is A cosine beta x plus B sine beta x. Okay, so by analogy, right, we can say that our wave function, or psi2 of x, can be written as A cosine kx plus B sine kx, where our constant k is given by 2me to the 1/2 over h bar. Okay, so again, same idea as we used before, right? We just have a different constant here. Okay. Okay, so now that we have our general solution for the particle in a box problem, we want to find our coefficients here, our A and our B, and hopefully you remember that the way that we find those coefficients is to then apply the boundary conditions for our problem. Okay, so applying our boundary conditions is going to be our next step. Okay, application of boundary conditions. So let's remind ourselves what our boundary conditions are. Okay, so here is our general solution to our particle in a box problem. Okay, first boundary condition we want to apply is at x equals 0. So if our wave function, we know that needs to be continuous at our boundary. Okay, that was one of our postulates. Okay, so we know that at x equals 0, our wave function has to equal 0, because remember in region 1, which is on the boundary between regions 1 and 2, okay, we want to have a continuous function, and we know that in region 1 our wave function is equal to 0, so that means that at our boundary of region 2 our wave function has to go to 0 in order to have a well-behaved continuous function. Okay, so boundary condition is at x equals 0, our psi of 0 must be 0. Okay, so if we plug in 0 wherever we see an x in our general solution, we end up with this equation, and now we just start evaluating it and see where we end up. Okay, so we know some things about cosine and sine at 0, so remember cosine of 0 is 1, sine of 0 is 0, okay, so that leads us to the conclusion that a cosine of kx is equal to 0. Okay, so that then leads us to the conclusion that our coefficient a is equal to 0, because we already know that cosine of kx is 1. The only way for us to get 0 then would be for our coefficient a to be 0. Okay, so there's the result of our first boundary condition. Okay, so now that we know that a is equal to 0, that leaves us with resulting wave function for our next boundary of x equals a of b sine of ka. Okay, so remember up here, since we have a equals 0, this part of our wave function is going to disappear. We're going to be left with this b sine kx term, okay, and then we're just going to plug in our second boundary condition, which is at x equals a. Okay, we know that our wave function also has to equal 0 there for the same continuity reasons that we had from before. Okay, so this time our regions 2 and 3 have to be continuous at the boundary, so we know that the wave function is 0 in region 3, so we know our boundary, at our boundary our wave function has to equal 0. Okay, so our wave function at a also has to equal 0 according to our boundary condition. Alright, so we have a couple of options for how b sine ka can equal 0. The first is if b is equal to 0, nice and easy, right? But that is not super interesting to us, because then that leaves us with a equals 0 and b equals 0, which means we have no wave function, and we've already said that no wave function means that we don't have a particle, which is not a very interesting problem for us to look at, so this is what we would call a trivial solution. Okay, so we want to see if we can find something else that will work. So other option will be to have the sine ka part of our expression to equal 0. Okay, that would also work for us. All right, and it turns out that that is true if ka is equal to integer values of pi. So we'll say that ka is equal to n pi. All right, so you can remind yourselves of where your sine function equals 0. So if you plot that, you'll see that you'll cross the 0 value at integer values of pi. Okay, so one caveat that we're going to put on there is that n can equal 1, 2, 3, and so on. Okay, it does also equal 0 at n equals 0, but if we put in n equals 0, then we get, again, our situation where we have no wave function equals not interesting, or again, another trivial solution if you want to use that lingo. Okay, so just rearranging here, we can solve for k. we can say that equals n pi over a, and then let's just plug that guy in up here, and then we will end up with our final expression for our wave function. Oops, not a. We'll put it in general terms back to x. Okay, we end up with b sine n pi x over a as our final expression for our wave function for a particle in a box. Okay, so here again we're just plugging back in our general x where we had our a. We just want to get back to our general form for our wave function. Okay, so just one more thing having to do with our wave function is this is not the final form of our wave function because we still don't know what our b coefficient is. So b is what we call our normalization constant. So we're going to walk through quickly how to normalize our wave function. So this is one skill that you're going to put into use over and over again. We like to work with normalized wave functions in quantum chemistry. So this is a skill that you're going to want to develop. So we'll walk through our first example together for a particle in a box wave function. Okay, so remember our Born interpretation where we introduce this idea of our probability distribution. Okay, so remember our psi star psi dx, we said should equal 1. Okay, if we are integrating over all space. Okay, so essentially what we're saying there is that the probability of finding our particle somewhere between negative infinity to infinity or over all space, right, must be 1. Okay, now when we're talking about a particle that is bound to a certain region, okay, all we want to do there is to adjust our boundaries. Okay, so for a particle in a box, we'll just say that the probability of finding our particle somewhere between 0 and a is 1, right? Because we know that our particle is destined to spend eternity inside of our box with infinite potential walls. Okay, so let's set up our normalization condition for the particle in a box. So again, our bounds go from 0 to a for our box, and then we're going to plug in our wave function. So psi star for us is just going to be our regular old wave function because our particle in a box wave functions are not complex. There's no I anywhere in our wave function, so we'll just put b sine n pi x over a for our psi star, and then once again for our psi. Okay, so we essentially have our wave function squared, our psi squared. Okay, and we want that to equal 1. Okay, so now what we're going to do is solve for b and see what b has to be equal to in order to make this expression true. Okay, so first thing we want to do is pull everything out of our integral that we can. In this case, that's just our b's. So we'll have b squared times the integral of sine squared n pi x over a dx from 0 to a. We know that equals 1. Okay, so now your next task would be to look up this integral in an integral table, or you can plug it into something like Mathematica if you're familiar with that, or really just find this integral in some sort of integral table. The inside cover of Macquarie should have a list of the commonly used integrals that you're going to encounter in our calculations this semester, so you should find this beauty in there. So when you do find that solution, you should find that that equals a over 2. Okay, so then we'll just plug that in. So we have b squared times a over 2 equals 1. We will solve for b squared. It's 2 over a, which means our b is plus or minus the square root of 2 over a. All right, so there is our, what we would call our normalization constant. Okay, and then we can put everything back together with our wave function. So we would have psi of x equals root 2 over a sine of n pi x over a. All right, so you do get clearly both the positive and negative roots there when you take the square root. Okay, convention for us will be to just use the positive value when we're writing out our wave functions. Okay, so this ends up being our final particle in a box wave function. Okay, and we will do some fun stuff with that with a Python exercise in class. So we'll get to play around a little bit more with visualizing those wave functions using Python.